Okay, today we are discuss about three gate question from 2013. So let's start one by one. Hi everyone. Now read the question first. The major product formed in the reaction given below is, so this is alpha beta unsaturated ketone and we are treating with organopyruvate followed by acidic workup. So what will be the product?
D sir.
Okay.
I'm
Let's
going
solve.
to discuss one gate question from gate 2013, question number 20. The major product formed in the following reaction given below is, so this is alpha beta unsaturated ketone, and in the beta position there is a tertiary ethyl group, and this is treated with methyl copper reagent in diethyl ether followed by acidic workup. So what is our product? So in the product we can see that that methyl group is added in two cases. In this keto group, I mean 1,2 addition is happening here, and the rest two cases and the addition is happening in the 1,4 position. So we have to find out which is correct, whether the 1,2 addition will happen or 1,4 addition will happen, and next we have to decide what will be the stereochemistry of this addition. So to know this, we have to first know what is this reaction. This reagent is basically known as Gilman reagent, where, see, this is the 1, 2, 3. Okay, and so this is sometimes this is called alpha beta, because this keto group is our directing group. This is alpha beta. So now the questions come whether our nucleophile will attack at this position or this position. That will decided by the our organo corresponding organo compound. If Rm, if metal is hard, then 1 to I mean 1 to addition will be happen. What will the 1 to addition? Then the name will start from here. 1, 2, 3, 4. 1 to addition. Or if the Rm is soft, that time 1 for addition. Okay. Or this is called also beta addition. So copper reagent, basically organocuprate compound are basically relatively unstable. So when this type of organic species which attach with copper, that become highly nucleophilic in nature, and copper is soft in nature, so that's why the addition will be happen at the fourth position, not the two position. That's why it is called 1,4 addition or beta addition. Okay, if our aim is magnesium bromide, then it will be 1,2 addition. So the nomenclature start from basically here 1, 2, 3, 4. So copper will attack here. So and we will get the corresponding carbonyl like this. Okay. So in this compound, our copper is soft in nature, so methyl group will attack this four position. 1, 2, 3, 4. Four position. So our methyl group Ame minus will attack here. Now the questions come after this attacking from which side this methyl group will attack. You can you can just seeing this group. This is a trick. You can predict that as the tertiary butoxide group is upper position, so due to the steady, the methyl group should come from the downside. So the product will be after that acidic workup. So this O minus will abstract a photon, and after that ketoenol tautomerism will happen, and we will get the corresponding keto because the keto is more stable than enol form. So methyl group will be here, and this group will be here. But the actual reason behind this is that this particular structure is basically adopt this half chair type conformation. Okay, and this is our tertiary butoxide group that will adopt p axial position. Okay. The actual reason behind this methyl group attacking from this downside is that because if methyl group will attack from the upside, it will adopt a twist boat conformation, and if methyl group approach from the downside, then it adapt a chair-like transition state. That is the main reason why the methyl group is approaching from the left side, not because of this tertiary butoxide group. Because if the tertiary butoxide group is in two position, the scenario is totally different. That time methyl and tertiary butoxide group in the same site. But as they are in beta with respect to keto group, that's why they will come just different side. Okay. So here the group should be come from this side because in this approach, this particular conformer will adopt a chair-like transition state. That's why that group is coming from the below phase. Okay. So our correct option will be option number D. So for more information, you can watch this NPTEL video. Thank you.
Is it clear?
Yes, sir.
So,
Hi everyone.
read the question then answer. The number of signals that appear in the proton decoupled spectra of 13C NMR spectra of benzonitrile, that is and 1 nitrile group. So how many signal we will get?
5.
Okay. And what is the meaning of the proton decoupled spectra?
All other uh, spectra like proton spectra are
Sorry, I'm not getting.
should not coupling with the hydrogen.
Okay, why it should not couple? Any reason?
Reason.
It resonate, but its spectral uh, frequency should very low.
No, no, actually
By
CH
apply,
coupling constant is normally 250 hertz. So more than proton. Normally proton coupling constant maximum is 18 hertz or 20 hertz. But CH coupling constant is around 200 hertz. But why it should not couple? So the reason behind is that we are basically irradiate the proton in such a way that the population of the alpha state and beta state will be the same. Okay, so alpha state beta state means same means there will be a no transition. So the neighboring carbon will see that there is no population difference in the alpha state and beta state. I mean there is nothing. That's why there will be a no splitting. That's why only 13 will be come as a singlet, not doublet, triplet. But there are many experiments like where the carbon can couple with hydrogen. Where suppose if we have CH moiety, then we see a doublet. If we have CH2 moiety, we will see a triplet like that. Okay.
now we're going to discuss one gate question from gate 2013, question number 24. The number of signals that appear in the proton decoupled 13C NMR spectrum of benzonitrile is, so we have to find out how many chemically non-equivalent carbon is there in the benzonitrile. So what is the structure of benzonitrile? This is the structure of benzonitrile, C triple bond N. Okay. Now, what is the meaning of proton decoupled spectra? We know that carbon-hydrogen bond, that 12C is I is equal to 0. So it is not, I mean, spin active. So, but 13C will show the spin is there, I is equal to half. So it will show splitting, but its abundance in nature is very less, around 1.1% with respect to 12C. So that's why this, when the 13C is there, so in 1H will also there, so they must couple, right? So what will, let's say if no group is there, some X is there, that time it must show doublet. But the meaning of the proton decoupled spectrum means that we are giving some irradiation to this hydrogen so that the alpha state and beta state population of this hydrogen becomes equivalent, so that the 13C will not split with, by seeing this hydrogen. So 13C will show only singlet, only one peak, but not a doublet because we are irradiating this 1H hydrogen. So the meaning of this question is that we have to find out how many different types of carbon is there particular in this compound. So for that we have to find out, is there any symmetry in this molecule. Suppose let's say if we have CH3, how many carbon is there? Two carbon is there, but we get only one peak because it has symmetry on sigma plane or C2 axis. If we take a benzene, six carbon is there, but due to the C6 axis, there is a C6 axis, right? Or sigma plane, too many sigma plane. Due to that, the all carbon becomes equivalent and we get only one peak. But what is the scenario in this case? Let's draw this molecule in big. So in this molecule, is there any symmetry? Yes, there is one sigma plane, only one sigma plane or C2 axis, whatever it is, sigma plane or C2 axis is there. Due to that, let's say number this 1, 2, 3, 4, 5, 6. Due to this plane, due to this symmetry, 2 is equivalent with 6 and 3 is equivalent with 5. Okay, so how many signal we'll get? How many different chemically non-equivalent carbon is there? So due to the symmetry, 2 and 6 become chemically equivalent. Okay, so start from here. So 1, 2, 3, 4, 5. Because, and this 4 and 4 will give the same signal. 3 and this 6 will give the same signal because they are chemically equivalent. Okay, so we can say that how, so total number of peak, how many peak we'll get? Well, we'll get 5 peak or 5 signals. So the number of signals that appear in the proton decoupled 13C NMR spectrum of benzonitrile is 5. So for more information, you can watch this NPTEL video. Thank you.
Is it clear?
Yes, sir.
Okay, okay.
Yes, sir.
Hi everyone.
If you're able to solve this question, I think you can solve any NMR question.
Option A, sir.
Okay. Any other answer?
C, sir.
Okay, you can solve this.
Now I'm going to discuss one GATE question from GATE 2013, question number 27. An organic compound Q exhibited the following spectral data: IR 1760 cm in Mars, 1H NMR, delta in ppm, 7.2, 1 hydrogen doublet, J is equal to 16.0 Hz. Remember, this is very much important thing. J is equal to 16.0 Hz. Then 5.1, 1 hydrogen multiplet, 2.1, 3 hydrogen singlet, 1.8, 3 hydrogen doublet, J is equal to 7.0 Hz. And 13C spectra, delta is equal to ppm 170, only one peak is there given, that is for carbonyl carbon. What is the compound Q? So in this compound, every compound has a carbonyl group. So it is difficult to say which is which. Okay, and so we have to go to the analysis. So now come to the analysis. So first one thing we have to see, if a double bond is there and this type of double bond and this type of double bond, due to this lone pair conjugation, this, so this will be, delta value will be So this carbon should be shielded because it will have more, so it will be shielded. So delta value will be low and its delta value should be high. And in this case, this delta value should be high and this delta value should be low, because in both case two different type of conjugation is there. In normal keto group, what is the value of the IR stretching frequency? Around 17-20 centimeter inverse in normal keto. Sorry, 40 centimeter inverse. But it is somehow greater in the stretching frequency. Okay. So we have to analysis each and every part. Okay. Now come to this. Now tell me, in this molecule, in this fourth molecule, the 7.2 and 5.1, that mass should be this double bond to olefinic hydrogen. This, or this, or this. Let's say I am drawing this molecule. Okay. So due to this 7.2 and 5.1, see, one is relatively high and relatively low. That means there must be some conjugation. And in every system there is conjugation. Here this type of conjugation. Here also same type of conjugation. Here reverse type of conjugation. Here reverse type of conjugation. Okay. Now come to this 16.05. That basically means due to the Karpfus fluorescence, this means that should be trans olefin. Now come, this is trans, that is possible. This is cis, so first eliminate this option. This possible, this possible. So option B, we can easily eliminate. Now come to the IR stretching frequency. If the IR stretching frequency is 70-40 normally for keto group, but this is conjugated ketone, so its stretching frequency should be less than that compound. Okay, so we can say that its stretching frequency should be less than 1700, less than, or I am writing less than 1700 centimeter inverse. Okay, so this is also not possible because its value should be less than 1700 centimeter inverse. Now only these two options is left. Okay, now we have to find out which one is correct answer. Now come to the next part. 2.1 hydrogen, 2.1 3 hydrogen singlet. So singlet, which group will show singlet? This group must couple with this, and this group also not will show singlet, and the value is 2.1. So that can be this group or this group. So singlet means in the both cases these two methyl groups should be singlet, right? Because they are isolated. So in this case, this group normally come around 4 ppm, and this group normally come around 1.9 ppm or 2 ppm. You can say also 2 ppm, because if you read the Claydon, there is one formula that is 0.9 plus 1. So around 2 ppm. So this is 4, this is 2, and the value is singlet. Where is the singlet? This is 2.1. So this is matching like this molecule. And come to the next part. 1.83 hydrogen doublet. 1.83 hydrogen doublet. That is in both cases that is possible. No problem. So by seeing this, only this particular thing, if the oxygen is directly attached to this methyl group, the value should be 4 ppm, and if it is attached to the keto group, the value should be 2 ppm. If you know this much only, I think you can able to solve many questions. So here the key point is that you have to remember that if methyl group is attached to directly ester, like this ester, this value should be 4 ppm, around 4 ppm, not 4 ppm exactly, of course. And the methyl group is attached to the keto group of this ester, then the value would be around 2 ppm. That is the most remembering thing. Always remember, because here the methyl is directly attached to the electronegative group, and here methyl is attached with carbon, then with electronegative group. That's why this type of observation is observed. Another reason is that due to this type of conjugation, oxygen gets somehow positive charge. Due to that also this methyl is somewhat desilate. Okay, I think it is clear now. So now we go to the analyze of this FD part. O C double bond O Me hydrogen Me. So due to this conjugation, so this proton should be most shielded. That means 5.1, and that will show multiplate basically because first it coupled with this hydrogen, first it will show doublet, and then it will show coupling with methyl. So it will show basically doublet followed by quartet, or simply we can say multiplet. And this group will show a doublet. What is that doublet value? The doublet value is 1.8. Okay, and the coupling constant is 7 Hz. What is that? This will show only coupling with this, and this type of allylic coupling is very less, around less than 1. So we can, and so that's why we can say that this is around 7.2, and the coupling constant is very high. How much? 16.0 Hz. Okay, and this methyl will show 2.1. Okay, so our correct option will be option A. So our correct option will be option A. So for more this type of information, you can watch this NPTEL video. Thank you.
Is it clear?
Yes, sir.
Okay, fine. Okay, read the question number 3. 3. No, it is not the one-thread hydrogen, one-thread diazo interaction. This is something different. Any other answer?
Anti-bonding orbital of trans Br with interactions with tertiary butyl group. That
No, no.
interactions
No.
increases the.
Tell. Let's solve it. So this is equatorial hydrogen and this is axial hydrogen, right? So forget about the question. Let's say one observation. At 90 degrees centigrade, cyclohexane show only one peak, 90 degrees centigrade. And let's say at minus 90 degrees centigrade, it shows two peak. What is the reason? This is the cyclohexane.
The functionality behavior of that isomers in minus 90 degrees Celsius is freeze.
Yeah, yes. So minus 90 degrees centigrade, it will be freeze. So that time axial cannot be converted to the equatorial. I mean, there is a rapid equilibrium, right? Sorry. It should not be like this. So this is axial and this is equatorial, right? And for this will be axial and this will be equatorial. Let's say this is one hydrogen, hydrogen number one, and this is hydrogen number two. So at that when it is flipped, so this time this hydrogen one is in equatorial axial position, but this hydrogen two will be equatorial position. So in one conformation, the hydrogen one is equatorial position, and another conformation, the hydrogen one is axial position. So when this type of equilibrium is there at 90 degrees centigrade, that time we will show only one peak. But at minus 90 degrees centigrade, this type of conversion will be freeze, restricted. That time axial will be always stay axial and equatorial say stay in always in equatorial. That's why we will show different type of peak. Now tell me why the axial and equatorial shows different type of peaks. I mean why they are not equivalent at minus 90 degrees centigrade? Why they are showing two peaks?
Axial is 90 degree to the plane of that cyclohexane ring,
Okay,
and
yes.
equatorial is 120 degree.
So their environment is different, right? Now tell me which one should be more shielded and which one should be less shielded. I mean which delta value should be high or axial or equatorial.
Axial is shielded and equatorial is deshielded.
Why? What is the reason?
Due to that, if we construct the cone of then inside that cone, axial hydrogen is present. Outside that cone, equatorial hydrogen is present.
Yes, right? This thing, right? So this is the scenario. Okay. So this due to this ring current, let's say if we numbering from here, let's say A carbon, B carbon, C carbon, due to this B C ring current, because we always see that anisotropy is present in the benzene ring, like pi system, but there is also anisotropy in single bond also. Due to this bond, this is in deshielded position, this equatorial group, and axial group is in shielded position. That's why the delta value is always higher in equatorial than axial. This is the true for everything. So equatorial delta value will be high than axial because due to the ring current. Okay. Now in our question, when there will be a tertiary butoxide group, that time it will lock the conformer. That's why we will see things. What is the question? See here, what is happening here in the A. So this is the conformation is locked here. Ring clearing is not possible because the tertiary butoxyl group cannot stay axial position in any case. This is the remember. If you see any question with tertiary butoxide groups, always put first tertiary butoxide group in the equatorial position. Tertiary butyl group cannot stay in axial position anytime. Okay, that's why this A and B will stay only this particular form. That's why this hydrogen is equatorial position. That means the delta value should be high. And in the option B, the H in the axial position. That's why it is 3.63. Clear? It is clear or not? Tell me first.
Sir, once again explain, sir.
You have understand this thing, right? This is cyclohexane. Cyclohexane can exist in this form or in this form at room temperature because at room temperature there is sufficient energy to convert from this type of conformation to this type of conformation. Let's say 1, 2, 3, 4. So 1, 2, 3, 4. So there is a rapid conversion at room temperature. Okay. So what we will see? We will see only one peak. What is the reason behind the only one peak? See, in this position, let's say we are numbering this hydrogen as a one hydrogen, this is as a two hydrogen. So each one hydrogen in this particular form, it is staying at equatorial position, and the hydrogen 2 is staying at axial position. So at room temperature, it can flick within 1 second. I mean, very less second. When the NMR time scale, less than NMR time scale. NMR time scale should do a minus 9 seconds. So less than 10 to the power 9 seconds, they is easily flip into this other form where we will observe that this equatorial becomes axial and axial become equatorial. I mean, one hydrogen in one case is equatorial and in another form it is axial. So we will observe a time average spectra. Time average spectra means that time average spectra. Okay, I will explain what is time average spectra. So another questions come. Let's say we have only one particular form. Let's say this form. We are lowering the temperature. So such that time the rim flicking is not possible. Okay, we let's say go to minus 90. That time rim, this type of rim flicking is not possible. That time axial will be always stay in axial and equatorial always stay in axial. And there is one concept that due to the BC, this particular bond ring current, it will, due to this ring current, this equatorial hydrogen always in delta value should be high because it is de-shielded position than axial position due to the ring current. Okay. So due to the ring current, this hydrogen, equatorial hydrogen is already de-shielded than axial. That's why its delta value should be high. Always. Remember, this is a universal truth. So now questions comes why you will see only one peak at 90 degrees centigrade, because equatorial is higher, delta value is high, and axial is here. So, so in the NMR time scale, they cannot, the NMR machine will be confused whether I will take equatorial or axial. So because this is suddenly changing, and they all are equivalent because due to this clipping, that time it will show a peak in the middle. So this is at 90 degrees centigrade scenario, because the ring is basically flipping. One time it is showing less value, and within same time scale it is showing upper value. So what NMR machine will capture the average value. But when that is in minus 90 degrees centigrade, that is confirmation is locked. That time NMR machine will show these two value. It is clear?
Yes, sir. Absolutely.
Yes, sir. Yes, sir.
Okay. So now in our question, what is our question? So now in our question, so they are basically that, say in the option A, I mean compound A, this is in equatorial position, and option B hydrogen is axial position. So equatorial will be high value than axial due to the ring current, and here the conformation is log due to the this tertiary butoxide group, tertiary butyl group. Whenever tertiary butoxyl group is present, that cannot be flipped into the axial. Okay, because here tertiary butoxyl group is there, right? Let's say bromine is there. If we try to flip this ring, what will happen? That time tertiary butyl group come in the axial position and bromine will come in the equatorial position, right? So
Yes, sir.
that time this tertiary butyl cannot group even present in axial position because due to the 1,3 diaxial interaction, never present. This is the, you cannot place tertiary butyl group in axial position at any time. That's why this particular conformation will be 100% and this is 0%. But at room temperature, I mean 90 degrees centigrade, that are in 100% and 0%. But here, this type of ring, this is 50%, 50%. Okay, that's why we will observe the difference. But here we cannot observe the difference because the system is already locked. And in the next part, the question is asking that if we replace the tertiary butoxide group with methyl group, that time again same scenario, the ring flipping is possible. So we will get different peak, except at lower temperature. Clear?
Yes, sir.
Yes, sir.
Okay, fine. Okay, I think we are at the end of this course. Okay. I don't know whether other TAs will be taking the class. I think this is the last class probably. Okay.
Thank you so much, sir, for all of your efforts.
No, thank you for joining. Uh, if there any question you can ask. And all the best for GATE exam.
Sir, can you drop your email ID?
Okay, I am writing it here.
Hey, hey.
soumyakantamajhi@gmail.com. Okay. soumyakantamajhi@gmail.com. So you can ask any question anytime. Okay.
Thank you so much, sir.
Any other question? If you want to ask, you can ask. And thank you also.
So stereochemistry point of view, which book we can refer, sir, for gate preparation? Because lot of questions, if you know the product also chemistry point of view, can't able to predict the product. Further, what practice we can do?
Okay, actually for the stereochemistry, when I was in BSc first year, I get a 0 marks in stereochemistry because I cannot able to visualize. Okay, stereochemistry is basically visualization. So you have to visualize the thing in 3D dimension. Okay, so you have to think actually. We have to first know how the bond is basically rotating. Take a molecule and rotate in different form. That is the first thing. If you can able to do that, and how the RS nomenclature. So in the RS nomenclature, you normally see that the molecule will they give in the exam in different form, so that your visualization should be needed there. So first thing you have to visualize, and if the you need the books, I will say the joyful. I mean for question answer. I mean what product will form with which stereochemistry, joyful and Clayton. I read these two books, and you have to read multiple times, not one time.
Okay, sir. Okay, sir.
Okay, first read the Clayton. I will better. Clayton is better. Language is
Yes, sir.
also good. Language is also good, but you have to give time actually. Otherwise, stereochemistry will be difficult.
Yes, sir. Yes, sir.
If you not good in organic, I will tell you that first start the spectra, organic spectra in good. There will be around 12, 15 marks from every question, right? 15 marks around. So do organic spectra in good. So there are no stereochemistry needed, nothing. So if you do that, that will be better. NMR, IR, mass and 13C. So in the mass, you have to know only two rearrangement, McLeod rearrangement and Dicelder rearrangement, and some 14 Korean bromine isotopic peak. That is enough for mass. And for the IR, normal station frequency like carbonyl. Most of the time they will ask question from carbonyl. That's done. And 1H and 13C, you need the concept. Otherwise, you cannot predict.
Yes, sir. Okay, sir.
Okay. Okay, is there any question? Then we can stop. And thank you.